Welcome back to the third part of the image processing and image analysis workflow. In this part, we will start with a new sample. So again, close my geodict and we'll start a new one. So we now again go into the import GeoVol module and open the new sample by clicking the browse button. In the folder containing the data you received, you will see there is another GRW file called air filter for micrometers, GRW. We click open. We see again everything is entered in this mask, and there is a size of 375 voxels in X and Y direction and 150 voxel in Z direction. And the voxel length is 4 micrometer. Now we open this file in image processing. As you can see, this is a fibrous media, and we again move around a bit things here to zoom in on the XY plane. So first of all, we disable the overlay, and you can see the fibers look as if they are hollow, and there's some noise in the pore space. The fibers look as if they are hollow, but they aren't actually hollow. So I confirmed this with our filtration expert, and what we see here is only an edge enhancement effect, because originally this CT scan had a much higher resolution. I sampled it down to get to a size that we can handle in this workshop here. So now if we want to segment this image, it is a bit harder, because if we try to use a simple threshold, you can see that we do not get the inner part of the fiber segmented correctly. So if I switch to manual threshold and try to increase the threshold, of course it gets worse and the fiber starts falling apart. If I go lower into the area where the inner part gets filled, we start to get a lot of noise in the pore space. So if I go to a value where basically all the inner parts of the fibers are filled, we don't see a lot of, where the pore space gets really noisy. So this is really unpleasant, and we want to avoid this effect. Now there's the option to go into a lot of image processing and try to get rid of the noise in the pore space and still have contrast to the interior of the pore, of the fibers. But that's a lot of work to get right without messing with your fibers too much. So what we will be doing is using the new AI-based trainable segmentation. So in the image processing, in the segmentation and labeling tab, open the image segmentation subtree and go into AI-based segmentation. Now, this method is probably well known to you. It's pretty common now, and a lot of tools implement this to where you basically label your image manually and then train some machine learning method to learn how to segment the whole image based on the labels you have provided. In our method, you can select between either a boosted tree method or a deep learning based method that uses a UNet in 2D or in 3D. The boosted tree method works pretty well for many examples and is really fast. Compared to this, the UNet model in general requires more training data, so you need to label more, provide more labels manually. But it has also the capability to better understand the CT scan and yield better results if enough training data is provided. For this workshop, we will use the boosted tree method, as the UNet method takes a lot longer to train, and also without a proper graphics card, it will take really long. So below the selection for the method, you can select the number of classes, so the number of material faces you have in your scan that you want to label. In our case, we will stay with 2 as we want to segment the pore space and the fibers. Below that is the switch for the mouse mode. So by default, we are in the navigation mode as we have been before, where you can click and hold to move the scan around or use your mouse wheel to switch between the slices. Next to that is the paint mode. That's the mode we will now switch into. And this will allow us to paint our labels onto this CT scan. Be aware when we enter the AI segmentation, the overlay automatically switched to AI labels, but maybe the visibility might still be turned down for you. So for me, it is fine. But if you now start to paint and don't see anything, then check this value up here. Yeah. So with the overlay in labels mode and in the painting mode, we can now start to paint. So for example, we paint a bit of pore space here in this noisy area. And then we switch to class 2. Now you see the ring that your mouse is painting has turned red. This means now we are labeling the red material face. Now our painter is a bit too big, so we decrease the brush size. Also to paint in these fibers, we want to zoom in. Now because we are in the paint mode, we cannot use the usual method to zoom in by pressing the right mouse button. Instead, we have to hold Shift and then hold the right mouse button to zoom in. The same is true for moving the picture. So we hold Shift, left click, then we can move the image. So down here, maybe to make the brush a bit smaller, we can paint a bit in the fiber. So be sure not to so it's kind of important to also label the boundary, but don't go too close to the boundary if you are not sure you're labeling it correct, because if you create false training data, that might induce some noise in the result. So now we can maybe zoom out a bit again, and we press the train button here. Now the training happens really fast because we have such a small sample and only a few training data. So the model is already trained, and we now have the preview button enabled here next to the train button. If we click it, then the preview is calculated, and you also see the overlay mode up here switch to AI preview. So now we see, yeah, that already looks pretty nice. So if we zoom in a bit again, also our mouse mode should be back to the navigation mode, and we can with right click move in. We see the segmentation is really good. There's basically no noise in the pore space, and the fibers look really nice. They are very well segmented. Also switch to the outline mode where you can see the boundary a bit better. So if the result wouldn't be that nice yet, we would continue to paint. So we go back over here, switch into the label mode again, and the mouse into paint mode. And then, for example, we could also paint a bit on the other slices. So right now we only painted in the XY slice, but maybe we also want to provide some labels over here. So I go into I paint pore again and zoom in a bit to make sure I'm not painting into the fiber, and paint a bit around here to make sure we have also in this direction everything captured. So for example, if you have a changing behavior in your image like a gradient or something, it is important to provide labels throughout the structure. Of course, you can also do some pre-processing, get rid of the labels. So now to get the results again, we click train again, And then we can again click on preview. See, the result is pretty much the same as the segmentation was already pretty good before. Now you can also save the labels you have created. So by clicking on Save Labels, you can save them to your folder. You don't need to do this because I already provided you some labels. So if you don't want to do more painting and you also want to get exactly the same results as I have, then click into Load Labels and select the Air Filter Training Data GLD file. This file contains some labels that I provided before. Now we should also switch the overlay back into label mode, and now we see there are a few more labels here that I have created beforehand. We train them again, and we have a look at the preview. It still looks good. And this means we are done with creating our model. And we could also save this model. So if you want to apply to maybe another CT scan that is very similar to this one, we could do this by saving the model and loading it later on. Now if we click on Create Segmentation, the model will be applied to each slice of the scan, and a segmentation will be created. A few things to note is that you need to take care of labeling each phase roughly the same amount, especially if you're training the unit model. And if you have more than 2 phases, then be sure to label the boundaries between each phase a few times. So if you have a boundary between phase 2 and phase 0, then provide some labels at boundaries between them and so on. Also for the unit model, we have the 2D and the 3D model. And the 2D one performs pretty well. It is by default looking at Z slices, but you can switch this around in the options. And they profit from labels being close to each other. So if you have a label an area, then put in as much labels as close to each other as possible to get a fully filled output window. So now for me, the segmentation with the boosted tree method is already done. And we have the result file open here again. And we minimize our image processing tab for now, and we can see the 3D image with the 2D view with the segmentation and the volume field. Can again toggle the visibility of the structure to compare the segmentation with the original image. And that already looks very good. Can now switch into 3D mode and disable our volume field to see the actual fibers. To highlight them a bit better, we can switch on outlines and halo. If for some reason the segmentation did not work for you, you can again click on Open Structure, go into the results folder and open the Air Filter Segmentation Structure GDT. Because we are confident in the segmentation we created, we can now remove the image from memory. So we click on the gray value image right here and right click it, and then click on Discard Image. Then the image is removed from memory because we don't need it anymore. And in the next step, we will analyze the fibers in this material. To do it, we click on Analyze and then on Fiber Find. And then we are in the module to analyze fibrous materials. There we have the possibility to analyze the diameter and the orientation, the curvature of fibers. And we have also, as in the Grain Find module, the option to identify individual fibers. We will start with the simple diameter analysis. To do so, click on Fiber Diameters and then click on the Edit button. In here, we can again choose the materials we want to analyze. We only have one solid material, so it's straightforward. We can also remove fiber fragments from the domain boundary, but we do not want to do this as basically all our fibers are touching the domain boundary. And up here, we want to change the result file name to air filter fiber diameters. Then we click on OK, and we click on Run. That analysis should be pretty fast. And we again get a result file. In that result file, we get the fiber diameter estimation to be 38.6 micrometers and a standard deviation of 3 micrometer. Can have a look at the plot. We can see the diameter distribution is pretty much focused on this narrow area here. We can also look at the fiber diameters in the structure by loading the size distribution in the data visualization tab. So click here. Then it will load the fiber diameter field. Now it tells us it doesn't want to visualize material ID 1 as it will overlap with the volume field. So we click yes, and material ID 1 is automatically set to hidden. Now we have still the color map from the image processing, so we switch in the volume field tab from gray value to default. We get the default color map from blue to red, and we see most of the fibers are in the area of 35 to 40 micrometers, and we have some smaller fiber diameters at the boundary. In the next step, we will analyze the orientation of the fibers. To do this, we switch in FiberFind from estimate fiber diameters to estimate fiber orientation. Click again on the edit button to set the parameters. First of all, we change again the result file from just fiber orientations to air filter fiber orientations. We again want to analyze all solid materials, and in this area we can subdivide the whole domain into multiple subdomains to get an orientation tensor for the fibers for each subdomain. So for example, if you have a layered structure, you can by this method analyze each layer individually. For our case, we only want one orientation tensor. Down here we can select the algorithm that is used to analyze the orientation. Both algorithms work pretty well, but the Starling's distribution algorithm, it's a bit more computational heavy, but also works for very badly segmented fibers. We will use this for now, and we also will write a GOF file. A GOF file is a geodict orientation file that contains orientation tensors in each voxel of the structure. So you can, for example, use this result in a solver to simulate direction-dependent conductivity. Click OK, and then we click the Run button again. This computation will take a bit longer than the previous one, but should also be done pretty soon. So now most of the computation has been done, and it's only averaging the orientation tensor for the one block we have defined. Now it's writing the orientation file. If you want to see detailed information, you can also click on this button to open the console here, where you will see some output of Geodict. So now we again are in the result viewer and have the result of the fiber orientation analysis. In this case, this is mainly the orientation tensor of the fibers. So we see we have a strong in-plane orientation with a bit more in the X than in the Y direction, and basically a planar orientation in the Z direction. We again want to visualize our results, so we load the orientation file. And now we have in our structure the orientation file. We go into the volume field tab and disable the visibility in the pore space. And switch the color, so the actual thing that is visualized, from phi to angle to x. This way will result in a visualization of the angle of the fiber to the x-axis. Now we can nicely see we have these fibers that are parallel to the x-axis at an angle of basically 0. And for example, that red one going from top to bottom parallel to the y-axis at basically 90 degrees. You can see this also if you turn the structure around. Here we have some fibers in the intermediate direction. And this field can be used by the solvers to compute direction-dependent properties. To get a nice impression of the distribution of the fibers in the different directions, you can click on the clip value here and switch it from phi to angle to x. And then we can move the slider around. You can see if you move it to the left, we see all the fibers. Now if we move it to the right, first the fibers in the x direction disappear, then the intermediate direction fibers disappear, so we only have basically the fibers in the y direction left, and if we move it all the way to the right, all the fibers disappear. For our final analysis, we will do the same that we did before for the grains and run the identify fibers algorithm. This method is an AI-based algorithm that labels all the fibers in the structure individually. So if you open up this dialog and you get an error message here, then your computer is probably not set up with a GPU powerful enough. You can also check this by clicking on the solver options tab in here. And for me now it reads suitable GPU found. For you, there might be that you only run in CPU mode. If you only run in CPU mode, this analysis may take too long, and you can instead load the result that was in the data folder. So in the main tab, we only change the threshold value down here from 0.5 to 0.35. We do not want to remove the boundary fibers, else we won't have any left. In the solver options, we won't do anything, and we don't need another fiber orientation file as we already looked at it. So this method can also compute the fiber orientation and the fiber diameter, but we already did this with the non-machine learning based options. Up here, we again change the result file from identify fibers to air filter identify fibers. Then we click OK, and we click the Run button. Now, if you haven't opened it up, maybe open up the console right here, and you will see the analysis working. So if this is very slow for you, your GPU might be too slow, or you're running in CPU mode, then you can just cancel it and instead load the result in the data folder. So this analysis now takes a moment. The first step is the neural network is analyzing the structure and identifying the center lines of the fibers. And afterwards, another algorithm is running to convert them into analytic representations. That's what's happening now. And now we are done. We again get a result file. In this structure, we have 442 individual fibers. We get the orientation tensor. We can now compare this orientation tensor to the one computed by the fiber orientation analysis. Click here on result, get the orientation tensor, And you can see they are a bit different, but overall very similar. Again, only click on the Identify Fibers result up here to remove the second result viewer. Below the orientation tensor, we get a mean fiber length of 800 micrometer. And if we go over into the plots tab, we can see the fiber length distribution, and we can nicely see the spike at 1500 micrometer here. That corresponds to our structure size of 375 voxels times 4 micrometer. It equals 1500. So these are all the fibers that are just going through the whole structure. Of course, we also have smaller parts that are cut at the domain boundary and a few bigger ones that are curled up. And finally, we can also look at the individually labeled fibers. To do this, we click on the fiber identification visualization and load the first file called Identify Fibers, load G32. Yes, we want to set the material to visible. Click OK. And click Yes again. And we can minimize our result viewer. And we get the individually labeled fibers as we've seen before in the grain find result. There are some boundary artifacts up here because the fibers are cut, but we can clip into the volume field using the clip slider in the volume field tab. And we can nicely see the fibers being individually labeled. Even here, the two ones that are running in parallel through the whole structure get separated nicely. You can also look at this in 2D. So now I'm already in the Z view. If you are not, you can go into the camera tab and select direction Z. And we can go into structure. We can see the fibers being nicely separated, even if they are touching in the original scan. So this will conclude the image analysis and image processing workshop, and you are now free to ask questions if you have any. And thank you for your attention.